So this is the website of a former UC math teacher, Vancouver, cool guy. And if you scroll down a bit, he has a 16C website. I think it's linked in Canvas as well. And if you scroll down here, he's got all kinds of homework problems that are definitely good problems to do. So if you're looking for more, or you're looking to do something your teacher hasn't posted any yet, I definitely recommend going here. So we're in section 10 now, right?
Yeah.
So like scroll down ways somewhere down here. Here's the second homework. Here's the homework. Section 10 homework problems from Kuba. And again, I'm pretty sure this is linked in Canvas. Let's double check. Okay, yeah, I don't care about all this. And okay, go away. Okay. Co-16C. Welcome, Ryan and Alexia. Let me give you the link for attendance if I can get it at some point. Yeah, sorry. We go to the syllabus. I think it's actually, guys, it looks really big. Yeah, Co-16C website right here in Canvas. So if you're looking for more problems to do or any problems to do, I recommend it. It's a good resource. There's something else I was doing. Oh, I know. I was going to look at his Canvas to see what. That's fine. We're good. Let me. I was also, yeah, I was doing this here. Sorry, not being distracted. What's your next test?
Next, yeah, so next Friday. It's right next week. Yeah.
Sorry, 1 second, folks, over here on the Zooms. Let me do the thing. There you go. Here's the attendance form. Please fill it out when you have a second. Let's see. So yeah, let's talk about series. Okay, so series. I guess I could write down other things here. Sorry, 1 second. Co-16C, day 15. So what's a series? Well, it's basically a bunch of numbers added up together, right? So typically when we're talking about a series, we're talking about an infinite series. So here's an example. Sum n equals 1 to infinity, 2n over n plus 1. And you can definitely write out some terms. It's usually not particularly useful. So we could say, well, if I start n equals 1, I get 2 over 2. And then n equals 2, I get 4 over 3. And then equals 3, I get 6 over 4. And so on and so on and so on. Forever and ever and ever. And typically, what we talk about when we talk about a series is whether or not the series converges or diverges. So a series converges if all the numbers add up to some finite value. The series diverges otherwise. So a series can diverge. So I guess I can write things down. Let me write things down. So series converges if the terms add up to some finite number. Series diverges otherwise. Series diverges if it doesn't converge. Now, I will point out, just because it's worth pointing out, there are many ways in which a series can diverge. It can diverge to infinity. In fact, this one here definitely does diverge to infinity. So this series here diverges to infinity. Here's what's happening. So if we look at the sequence for a second. So here, I would say the series is the sum from n equals 1 to infinity of 2n over n plus 1. That's a series. And the sequence is just what we're taking the sum of. The sequence is, I'm going to call it a sub n, is 2n over n plus 1. So the difference between a sequence and a series is the sequence, you're just listing the terms with commas, essentially, whereas the series, you're adding up all the terms of the sequence. If you look at the sequence, the limit of the sequence is what? What's the limit as n goes to infinity of 2n over n plus 1? Everybody, show me on your fingers. Show me on your fingers. What's the answer to this question? What's the limit as n goes to infinity of 2n over n plus 1? You only need one hand. Yeah, that hand. Yeah. That limit is definitely 2. We know it's 2 because of that, the kind of the trick where you're like, oh yeah, the top thing and the bottom thing have the same degree, the same highest power of your variable n. So the limit is just the quotient of those leading coefficients, 2 over 1. Just like the limit as x goes to infinity of like 2x squared plus 5 over 3x squared plus 7 is 2/3. But here's what's happening. That means way out here, like we go way out to like the 100th term, like say 200 over 101 plus 202 over 102. Sorry, 202 over 100 and apologies, 100. That's right. I'm just, yeah. Right. These terms here, that's pretty much 2. Right. I mean, it's not exactly 2, but it's very close to 2. And there's a lot of terms out to the right here that are also very close to 2. And now here's the big question. How many numbers that are pretty close to 2 are we adding up? An infinite number of 2s. If you add up 2 plus 2 plus 2 plus 2 an infinite number of times, what are you going to get? So the deal here is that since this limit of the sequence is 2, we can say that the series itself, n equals 1 to infinity, 2n over n plus 1, diverges. And we could be more specific, and sometimes, well, no, usually the only times we're really asked to be more specific in this class is if you're doing web work. Sometimes that web work will ask you which way it diverges. This does diverge to infinity, but that's not always how something diverges. So this diverges because all the terms add up to just 2 plus 2 plus 2 plus 2 going to infinity. But this would be true no matter what non-zero limit the sequence went to, right? It wouldn't have mattered if it was 2 or a half or a millionth or a billionth. If you add up 1/1 billionth, an infinite number of times, you are still going to get infinitely large. This is where the nth term test or the test for divergence is actually coming from. Saying, oh yeah, if the sequence doesn't add up, if the sequence doesn't converge to 0, the series has to diverge. So that's actually the nth term test. The nth term test says if the limit as n goes to infinity of your sequence is not equal to 0, then the series from n equals 1 to infinity of that sequence must diverge. Or as I sometimes phrase it, for the series to even have a chance at converging, the limit of the sequence has to be 0. So usually, what's a good comparison here? It's kind of a good comparison. So whenever I am trying to see if a series is convergent or divergent, I'm always going to kind of check the nth term test and just be like, really quickly, does that limit go to 0? Yes, great, I'll move on to do some other tests, which we'll learn about. No, great, the series diverges, I am done. So it's kind of like, no, it's not kind of like, I'm trying to think of a good example. It's kind of like, it's not really like anything else. So if the sequence converges to not 0, or really, I should say, doesn't converge to 0, then and I really should use, if the limit of the sequence is not 0, then the series diverges. Excuse me, just as a kind of another point here. Here's another example of a series that's divergent. The sum from n equals 1 to infinity of -1 to the n. Kind of a classic example. I will point out you could show that it diverged by the nth term test, because the limit as n goes to infinity of -1 to the n is what? What is it? Definitely does not get infinitely large. If you plug in, like you pick a big number for n, what's -1 squared? What's -1 cubed? How about the fourth? How about the fifth? So the thing is, this sequence just keeps going back and forth between 1 and -1, 1 and -1, but it never picks one value over the other. So this limit actually does not exist. But not existing still is not equaling 0, right? That limit does not equal 0. This series diverges. Now I will point out, if you look at this series, the first term is -1, the next term is 1, the next term is -1. You're just adding and subtracting 1 every other time. But we're not getting close to, like, so -1 plus 1 is 0, -1 is -1, plus 1 is 0, -1 is -1, plus 1 is 0, -1 is -1, plus, right? You're going back and forth between two different sums, but you're never getting closer and closer to one particular thing that this whole series is adding up to. So this series definitely diverges. I will point out it does not diverge to infinity, right? The things we are adding up are not getting larger and larger and larger. Thing diverges in an oscillating or alternating kind of way. So you don't have to go add up to infinity to be divergent. That's just one of the ways we talk about being divergent. Cool. Let's look at a few more examples. What about the sum from n equals 1 to infinity 6e to the n over 2e to the n plus e to the -n? That was terrible. Who came up with that? Always does it. So sorry, there's a question. I'm assuming you're talking about this example right here. If the series added up to 0, we would actually say it converged to 0. But this definitely does not diverge to 0. It just diverges. Now, there's kind of something I'm glossing over because we don't typically talk about it in this class, but I feel like I can, yeah. So when you're talking about whether a series converges or diverges, what you're actually really doing is talking about whether the sequence of partial sums converges or diverges. Did he talk about that in class? I don't imagine he did, but he might have. You would definitely know if you heard those words. So I'll come back around this, but here I'll just point out the sequence of partial sums is just literally, so for this series, the sum from n equals 1 to infinity of -1 to the n, the first partial sum is just -1. I'm just adding up the first term to nothing else really, it's kind of done. The second partial sum is the first two terms added together. So it's -1 plus 1, which is 0. And that's a1 plus a2. I'm adding up the first two things. The third partial sum is a1 plus a2 plus a3, which is -1 plus 1 plus -1, which is -1. The fourth partial sum is going to get kind of boring here. That's going to be -1 plus 1 plus -1 plus 1, which is 0. So here, the sequence of partial sums is an alternating sequence between -1, 0, -1, 0, -1, 0. Okay, you did this a little bit in class, but this sequence doesn't converge, right? If you try to take the limit as n goes to infinity of this nth partial sum, that limit doesn't exist, right? You're just bouncing back and forth between two different numbers. And when we have that sort of sequence, you don't get a convergent sequence, you get a divergent sequence. So this limit does not exist. But the limit of the sequence of partial sums not existing means that the series itself doesn't add up to anything. It diverges. So that's really what you're actually doing when you're trying to show if a series converges or diverges. What you're really, or could be doing, is looking at the sequence of partial sums and asking, does the limit of that sequence of partial sums exist or not? And we'll do this a couple other times. I'll give you, we'll do this again. I'll give you another example of one that actually does converge. I think it's kind of nice. It's not too hard to see. So let's look at this for a second. Well, again, I'm really just looking at the nth term test every time. I always want to think about the nth term test just to make sure I don't miss something easy. And if I look at that, well, if I divide everything by e to the n, I get the limit as n goes to infinity of 6 over 2. And e to the negative n divided by e to the n is e to the negative 2n. Or if you prefer, e to the negative n over e to the n is 1 over e to the 2n. And then as n goes to infinity, e to the 2n goes to infinity, and 1 over e to the 2n goes to 0. So limit of this is 6 divided by 2, which is 3. You know what 3 is? Well, you know what 3 isn't? It's not 0. If it's not 0, that means this series diverges. Because what you're kind of doing here is you're adding up 3 an infinite number of times, and that gets you infinity. Okay. Let's look at a couple. Yeah. So let's say we had, yeah, let's do that one. Sure. Yeah. Let's say we had this sum from n equals 1 to infinity of 2 over n minus 2 over n plus 1. This is an example that you might not actually see in class, but it's fine. It's a good example anyway. This is an example of what's called a telescoping series. Let's write out some terms. So I get 2 over 1 minus 2 over 2 plus, now if n equals 2, I get 2 over 2 minus 2 over 3 plus 2 over 3 minus 2 over 4 plus 2 over 4 minus 2 over 5. If you look at this, things cancel. Negative 2 over 2 plus 2 over 2 cancels out. Negative 2 over 3 plus 2 over 3 cancels out. Negative 2 over 4 plus 2 over 4 cancels out. The negative 2 over 5 cancels out of the next thing. So it seems like this might just add up to a 2. It actually does. Now, let me point out, and this one might be the last, we might do this one with this. Let me show you kind of what the actual thought process here is. Let's find the partial sums. So the first partial sum is just the first term. Just to be super clear what I'm doing here, I am always using capital S for my sequence of partial sums, and I'm using lowercase a for the the sequence of terms. So what I'm really saying here when I'm writing this is a sub n is just the sequence 2 over n minus 2 over n plus 1. And S sub n is the sum of all the sequence terms up to n. So S2 is going to be A1 plus A2, which is 2 over 1 minus 2 over 2, plus 2 over 2 minus 2 over 3. And I can cancel some terms, and I get 2 minus 2 over 3. If I don't want to simplify, let's do 2 more. The third partial sum is A1 plus A2 plus A3. That's going to be 2 over 1 minus 2 over 2, plus 2 over 2 minus 2 over 3, plus 2 over 3 minus 2 over 4. All the middle things cancel. That cancels and that cancels. And I'm getting 2 minus 2 over 4. Okay, let me ask you all. For the fourth partial sum, which is going to be A1 plus A2 plus A3 plus A4, not writing out all these terms here, what do you think the answer is going to be at the end? Instead of 2 minus 1 and 2 minus 2/3 and 2 minus 2/4, it might be exactly. We're starting to see the pattern for the sequence of partial sums, and it is 2 minus 2/5. And I will point out that we can then write the nth partial sum. Well, it's going to be 2 minus 2 over what? Exactly. And now we can take the limit of the sequence of partial sums. So the limit of this sequence of partial sums, well, that's going to be the limit as n goes to infinity of Sn, which is the limit as n goes to infinity of 2 minus 2 over n plus 1. And as n goes to infinity, 2 over n plus 1 goes to 0. So this ends up being 2 minus 0, which is just 2. So we're not typically going to do this, right? We're not usually going to find what a sequence a series converges to, but it is possible to do some of the time. The point that I want to make, though, is that when you're talking about a sequence, you're talking about a series converging to a value. So this series here really does, I'm just going to write over here, this series, the sum from n equals 1 to infinity of 2 over n minus 2 over n plus 1 does converge to 2. What you could be doing to show that is finding the sequence of partial sums and then taking its limits. And that's kind of the idea behind when a sequence is convergent. We're not usually going to do that, but I just want you to know that that's really the idea, is you're not just saying the series adds up to this number. You're really saying, oh, you can find this pattern for this sequence and then take the limit of it and get that value. Kind of weird, but it's totally fine. So that said, we're going to move past that really, and we're going to talk about some other tests for showing whether a series is convergent or divergent. You have one of them already, the test for divergence, or the nth term test. Here's another good, here's a tricky example. Here, so what about this sum from n equals, n equals 1 infinity of 1 plus 1 over n to the n. This is a great, I'm a fan of this example. So when you don't know what to do, and we don't really know what to do because you don't have any tests yet, throw the nth term test out. I would always recommend, at least in your mind, try and take the limit as n goes to infinity of your sequence. What's that limit equal to? You know it's not equal to? 0. How do I know it's not 0? Well, I've got a number that's 1 plus something. This number is bigger than 1. And a number bigger than 1 raised to any positive power is for sure going to be bigger than 1. So I might not actually know what this is, but I know that it definitely is bigger than 1. And being bigger than 1 means you're not 0. So this definitely diverges. However, I really did want to actually point out what this limit was, because I do think it's worth knowing. This limit as n goes to infinity of 1 plus 1 over n to the nth power is e. Definitely. What to say about that?
Why is that 1?
Well, is that so? Think about it this way. Well, let's see. There's a lot. Let's see. Let's see. I don't want to get too into this, but it's definitely bigger than 1 because the numbers are bigger than 1, right? So if we start making a list of values, 1 plus 1 over n to the nth power, you plug in 1 plus 1 is 2, 2 to the 1 is 2. If you plug in 2, you get 1 plus a half, so 3 halves squared, which is 9/4, which is 2.25. If you plug in 3, right? It's definitely moving away from 2. It's getting bigger. Nothing. You could actually show this limit's equal to e using the L'Hopital's rule. It's a bit of work and not really the point. But it is true very generally that if you have the limit as n goes to infinity of 1 plus essentially something going to 0, and you have the reciprocal of that thing up here. So I've said specifically 1 over n and n, you're going to get e. But you can even be more general and say limit as n goes to infinity, say like 1 plus x over n to the n over x is going to go to e to the x. It's not super duper important, but it is a little important. Okay. Let's look at some more examples. I would guess he might have talked about this example in class, although he might not have. The sum from n equals 1 to infinity of 1 over n. Did you talk about that one? It's a pretty classic example. It's kind of like the most important example we probably ever see in this class. Maybe not the most. It's pretty important. That's 1 plus a half plus a third, fourth plus all the way forever and ever and ever. And definitely, if you try to throw the nth term test at it, it doesn't give you anything. The limit as n goes to infinity of 1 over n is for sure 0. What does that mean? It means nothing. It means that the series could converge or it could diverge. So when the limit's 0, that means the series could do either thing. Could converge, could diverge. Basically, this is one of the situations where when you see this sort of thing, what it really means is you have to do more work. That's what that really means. So when the limit of the sequence is 0, that means we have to do more. I don't think we talked about the integral test in this class. So did he show you how this goes? Did he show you all that this diverges? He did? I wonder how he did it. So here's one way of showing that this series is divergent. Check this out. I'm going to write some terms here. I'm going to write a lot of terms, actually. You might not want to write all this next part down. You might, though. It's kind of neat. Let's see here. Let's have to make sure I think about this right. 1 plus a half, plus I'm going to group these next two pieces together. A third plus a fourth, plus fifth, plus a sixth, plus a seventh, plus an eighth, plus a ninth, plus a 10th, all the way to a 16th, plus a 17th, all the way to a 32nd, and so on. So basically what we're doing here is we're kind of grouping every next power of 2. So here I will point out that there are 2 things. Here there are 4 terms. Here there would be 8 terms, right? 9, 10, 11, 12, 13, 14, 15, 16. It's kind of tricky though, because if you do 16 minus 9, you get 7. Right, but 16 minus 9, you have to add 1 back to actually know how many numbers there are. Kind of like a calendar counting problem. So there's 8 terms there. There's definitely 16 terms here, and so on. Okay, here's what I want you to see. These terms here, 1/3 plus a fourth, 1/3 is bigger than a fourth. True story, right? A third is bigger than a fourth. Have you seen that meme or whatever about how like Americans like didn't like buying a 3rd pounder because they thought it was a smaller burger than a 1/4 pounder? What's like why some McDonald's or whatever Burger King failed? Yeah, because some people think a 1/3 is not bigger than a fourth. A 1/3 is definitely bigger than a fourth. Okay, so this whole thing right here is bigger than a fourth plus a fourth. What's a fourth plus a fourth? A half. And this whole thing here, well, each of these terms is bigger than 1/8. So 1/5 plus 1/6 plus 1/7 plus 1/8 is bigger than 1/8 plus 1/8 plus 1/8 plus 1/8. How much does that add up to? A half. These terms here, what do you think they're going to be bigger than? 16 plus a 16 plus a 16, 8 times is a half. Each of these things that I've sectioned off is bigger than a half. How long can I do that for? Forever, right? I'm never going to run out of terms. I can grab the next 32 terms, and then the next 64 terms, and then the next 128 terms, and I can keep doing that literally forever. But that means I have this is bigger than 1 plus a half, 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 and you never run out of halves. And what's a half plus a half plus a half plus a half an infinite number of times? I think that's infinity. So that's one way of showing that this series diverges because you can show that you are adding up 1/2 an infinite number of times. Yes, you do have to grab twice as many terms every next time you want to get a half, but there's always going to be twice as many terms as there were before because there is an infinite number of terms. So this is how one way of showing that the harmonic series, which is what this series is called, so the series from n equals 1 to infinity of 1 over n, called the harmonic series, diverges. Even though the limit of its sequence was 0. So I really want to stress here, the limit of the sequence being 0 means the series could diverge. It also means the series could converge. And so you have to do more work when the limit of the sequence is equal to 0. Now, let's see, where are we going next? Sure, let's talk about, we got time. Oh, yeah, we got plenty of time. Let's talk about geometric series. Yeah, geometric, yeah. Cool. Cool. Geometric series. What makes a series a geometric series? Basically, each subsequent term is the same multiple of the previous term. So we get from term to term by multiplying by the same number, by some number, which we usually call R, or ratio. I should say some constant number R. For example, probably the most well-used geometric series, the sum from n equals 1 to infinity, 1/2 to the nth power. If we start writing out terms, we get 1/2 plus 1/2 squared is 1/4. Also, I will point out, when you have a geometric series like this, or any series where you have 1 over something to the nth power, you could also write it as just 1 over 2 to the n, because 1 to any power is just 1. So sometimes you'll see it written like this, sometimes you'll see it written like this. They do literally mean the same thing. All right, and then the next term is, going to be 1/2 cubed, and then 1/2 to the 4th, and so on and so on and so on. And what I want to point out is that what makes this geometric is that each next term you are multiplying by, in this case, the ratio of 1/2 to get there. 1/2 times 1/2 is 1/4. 1/4 times 1/2 is 1/8. 1/8 times 1/2 is 1/16. 1/16 times 1/2 is 1/32. So that's what makes it geometric, is that each next term is the same multiple of each previous term. Cool. So, yeah, let's do it this way. So here's another example of how we're going to show that this thing converges. We are going to find the sequence of partial sums here. It might be probably one of the last times we'll do it, but it's kind of nice. So let's add things up. First partial sum is 1/2. Not very exciting. Second partial sum is 1/2 plus 1/4, which is 2/4 plus 1/4, which is 3/4. Third partial sum. So let's be smart about this. Instead of writing 1/2 plus 1/4 plus 1/8, I mean, I guess I could write 1/2 plus 1/4 plus 1/8. I could have just said, well, I know the 1/2 and 1/4 already add up to 3/4. So I could have just said it's 3/4 plus 1/8, and then 3/4 is 6/8 plus 1/8, 7/8. But now when I do the next term, instead of writing 1/2 plus 1/4 plus 1/8 plus 16, I'm going to be smarter and write just 7/8 plus 1/16. And then that's 14 8/16 plus 1/16 is 15 16. And I feel like we might be starting to see what the pattern is. If you had to guess, you all could probably guess the next term is going to have what denominator? 32. And what numerator? Right. Because it looks like each denominator is just the next power of 2, and each numerator is always just 1 less than that. So to me, if I had to guess, it looks like the nth partial sum is going to be, well, the denominator is 2 to the power that we have the subscript, right? 2 to the 5th is 32, 2 to the 4th is 16, 2 to the 3rd is 8. And it looks on the numerator, it looks like it's just 1 less than that. And instead of trying to take the limit of this and having to do something like use L'Hopital's rule, let's be smarter and let's write this as 2 to the n over 2 to the n minus 1 over 2 to the n. It's really just 1 minus 1. So if you take the limit, it then goes to infinity of 1 minus 1 over 2 to the n. Well, clearly 1 over 2 to the n is going to get really, really small. You're just going to get that this is 1. So this series converges to 1. Sum from n equals 1 to infinity, 1/2 to the n equal to 1, or converges to 1. Usually, you just have to say that the series is equal to a number, and when you write that the series is equal to 1, or series is equal to 7, or series is equal to whatever number it's equal to, everyone knows you mean that the series converges to that value. You don't usually have to write those words. Okay. So, geometric series. Let's talk more about them. Because this is just one example. There's lots of examples. So let's look at another example. Let's say we have the series from n equals 1 to infinity of 5 times 3 to the n. I will point out that this sequence, sorry, this series, what was I going to point out? Something. The series is not 15 to the n, right? 5 times 3 to the n, you can't multiply and then raise it to the nth power. So I just want to make sure everyone's cool with the fact that this is not 15 to the nth power. Different things. I start writing out terms. I get 5 times 3, and then 5 times 3 squared, and 5 times 3 cubed, so on and so on. I could actually write the numbers if I really wanted to. That's what 15 plus 5 times 9 is 45, plus 5 times 27 is some number I don't care about anymore. It's 135. Is this geometric? For sure. What am I multiplying by? What 15 times what gets me 45? Right. 45 times what gets me 135? 3. Every time it's times 3. It's always the thing that's raised to the nth power. So if you have something like this, 5 times 3 to the n, your ratio here is 3. That's the thing you're multiplying by each time you get the next term. Okay, does this series converge? Well, what's happening? Look, forget the series. What about the sequence? 5 times 3 to the n, that's just getting bigger and bigger and bigger. Right? The next term is going to be 405, and the next term is going to be 1215. Right? The terms are getting really large. They are definitely not getting closer and closer to 0. So you could show that this series diverges because the sequence has a limit that is not 0, or the limit of the sequence, I should say, the limit of the sequence is not 0. This definitely diverges because the limit as n goes to infinity of the sequence is not 0. It's actually infinity. So let me show you. Yeah, we got time. It's fine. Let me show you something kind of cool, I think. So let's say we have a very so here's kind of a general format for a geometric series. A general geometric series looks like this. Sum from n equals usually 1, although really you can start actually anywhere you want, to infinity of sum a times sum r to the nth power. That is your usual format. So if you write it out, you know, it's a times r plus a times r squared plus a times r cubed, and so on and so on. Forever and ever and ever. Yeah, Annoyingly, we like to start at 0, though, but whatever. Okay, so check this out. I think this is kind of neat. I could be wrong. So let's say I wanted to find the nth partial sum and then find the limit. So here's how I'm going to find the nth partial sum. It's kind of a trick. You probably don't need to write this down. You might want to, but you probably don't need to. So let's say I want to find the nth partial sum. So let's say Sn is going to be the sum of the first n terms. So a times r for the first plus a times r squared plus a times r cubed, all the way to the last two terms, a times r to the n minus 1, a times r to the n. And then I'm going to multiply that whole sequence, that whole sum, I guess, by r. So r times Sn. Now I'm going to offset it just a little bit. So I multiply each of these terms by r times a times r is going to be a times r squared. And the next one will be a times r cubed. And I'll get a times r to the n minus 1. I'll get a times r to the n. And my last term will be a times r to the n plus 1. Essentially, each term has one higher power of r. Makes sense. Everything got multiplied by r. And now what we're going to do, we're going to subtract them. And notably, a lot of things are going to cancel out. Sn minus r times Sn, well, pretty much everything cancels, right? That cancels, everything that's lined up cancels. And we're just left with a times r minus a times r to the n plus 1. Okay, now I'm going to factor out the Sn. So Sn times, wow, let's show you your work there, James. Sn times 1 minus r. And also on the other side, I might as well factor out the a. The a times r minus r to the n plus 1 over, not over anything. Getting ahead of myself. And then finally, solving for Sn, you get a times r minus r to the n plus 1 over 1 minus r. Let me do one more thing to make this look a little bit nicer. So Sn is equal to, I'm going to factor out an r from the top as well. A times r times 1 minus r to the n over 1 minus r. Okay, so check this out. This is the formula for the nth partial sum. So the first n terms literally added to this amount. Okay, if I want to take the limit of this, the only part that really actually matters is going on right there. So here's what's kind of neat. So for this series, n equals 1 to infinity of a times r to the n, the nth partial sum is a times r times 1 minus r to the n, or 1 minus r. If I take the limit, n goes to infinity of this thing, well, if r is bigger than 1, like if r was 2, what's going to happen if r is 2? Well, 2 to the nth power is that getting really, really big or really, really small? As n gets larger and larger. Big. So if r is bigger than 1, r to the n gets infinitely large, which means this thing wouldn't converge because this would get infinitely large. It's also true if r is less than -1. A negative number, it doesn't go to infinity, but it does bounce back and forth between larger negative numbers and larger positive. Actually, I'll say r to the n doesn't go to 0. I think about like -3 to the nth power. Negative 3 to the nth is going to be -3, and then +9, and -27, and +81, and -243, and +729. It just gets bigger and bigger with negatives sometimes. On the other hand, if r is a number between -1 and 1, not including -1 and 1, like 1/2, what's 1/2 to the nth power as n gets larger and larger? Well, 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2 is getting very, very small. And it's true whether it's a positive 1/2 or whether it's a negative 1/2 or a negative 1/3 or a positive 4/5 or a negative 3/8. Anything that's between -1 and 1, if you raise it to a higher and higher power, gets smaller and smaller and smaller. So if r is between -1 and 1, then r to the n does go to 0. Which means that this thing is going to converge to a times r over 1 minus r if r is between -1 and 1. Or, as people usually write it, the absolute value of r is less than 1. That is a number. So, for example, if I wanted to find the sum from n equals 1 to infinity of 5 times 1/3 to the n, well, I know it's convergent. Well, first of all, I know it's a geometric series. Is geometric. And you all should be able to tell me what is my ratio. Everybody. You only got two choices, 5 or 1/3. It's definitely 1/3. The thing that's being raised to the nth power is always what your ratio is. Now, I'll point out, you can't have any other n's. Like, just for example, I want to tell you all, this series over here, the sum, wow, that's a terrible summation, but whatever. Sum from n equals 1 to infinity of, like, say, n times 1/4 to the nth power is not geometric. That n there is jamming things up. It can only, basically, to be geometric, you have to have this format. Some number a times some ratio to the n power. Anything else is off limits for to be geometric. You can also check, right? When I start writing out terms, my first term is 1 times 1/4. My next term is 2 times 1/4 squared. My next term is 3 times 1/4 cubed. And notably, I can't multiply this by something. Well, I can. 1/4 times 1/2 gets me 2/16, but 2/16 times 1/2 doesn't get me 3/64. So you're not multiplying by the same ratio each time, so it's not a geometric series. Cool. This is a geometric series, and your ratio is 1/3. And since your ratio is between -1 and 1, this series converges. So this series does converge. And I will say most of the time, as we move forward in this last section here, we are not going to know what the series converges to. There are lots of series that converge that we don't know what they converge to, but we do know they converge. The geometric series are kind of the exception to the rule. The geometric series, if it converges, we can always figure out what it converges to. In this example, this is going to converge to, let's see, 5 times 1/3 over 1 minus 1/3. Just like this series converged to a times r over 1 minus. In this example, our a is 5, our r is 1/3. Well, I'm gonna say more about that. So don't get that too stuck in your head, because I want to be more specific. Actually, I want to be more general. So that's gonna be 5/3 over 2/3, which adds up to 5/2. So this series is a convergent geometric series, and it converges to 5/2. Okay. So here's what I will say about convergence. So I've actually given you kind of an off-brand version of this formula, to be perfectly honest. I've never done it this way. I kind of happen to turn out this way. It's okay. But let's talk about a couple things in the last 2 minutes here. I will definitely give you a formula for this before we end. I want to say two things. First of all, definitely divergence of r is, right, we said the things here. Divergence of r is bigger than 1, or r is less than -1. Convergence of r is between -1 and 1. But what if r is equal to 1? Well, okay, what about the sum from n equals 1 to infinity of 1 to the nth power? Well, that definitely diverges, right? You're adding up 1 plus 1 plus 1 plus 1 plus 1 plus 1 an infinite number of times. That diverges. And similarly, if r is equal to -1, we already talked about how this series diverges, right? That one also diverges. So here's what I'll say. The sum from n equals 1 to infinity of a times r to the n converges if R is between -1 and 1, or we say the absolute value of R is less than 1, you can, if you prefer, you can totally write it like that. And diverges otherwise. Diverges if the absolute value of R is greater than or equal to 1. So R is bigger than or equal to 1, or R is less than or equal to 1. And if a geometric series converges, now here's what I want to say about this. A lot of times when you're talking about geometric series, some people will start at 0 instead of 1. So sum from n equals 0 to infinity of a times r to the n converges to a over 1 minus r. This one I wrote converges to a times r over 1 minus r. But here's what I really want you to know, because this is the best way to do it. The best way to think about what a geometric series converges to, if it converges. So if the absolute value of r is less than 1, then your geometric series, a times r to the n, converges to whatever the first term of the series is, divided by 1 minus your ratio. So if you start at n equals 0, your first term is a times r to the 0, which is just a times 1, which is a. If you start at n equals 1, your first term is a times r to the first, which is just a times r. But you could start at n equals 17, right? So I will point out the sum from n equals 17 to infinity of a times r to the n is a times r to the 17th power over 1 minus r. Or for a more nice, I know it's 201, I'll wrap it up here. For a nicer example, the sum from n equals 5 to infinity of 4 times -1/3 to the nth power is geometric. My ratio is -1/3, and this is definitely going to add up to or converge to my first term, which is 4 times -1/3 to the 5th over 1 minus my ratio, which is -1. And then you can simplify that if you feel like it. But that formula always works for finding what a geometric series converges to if it converges. And it's much easier than trying to do something dumb where you're like trying to make it start.